and welcome to this session. We will have a 90-minute session, and this is a co-hosted session from UNEP Global Partnership on Nutrient Management, together with Norwegian Research Center, Norse, about the AQUAPHOENIX project, how to turn waste into value, and especially focusing on the circular solution that can boost food production. My name is Per Larssons, and I will moderate today's session. I'm also a member of UNEP GPMM in the steering committee, and also serve as a Chief Sustainability Officer for Ragn-Sells Group. And we are serving the fish industry in Norway with waste management. But what we have done over the years, and I will come back to that, and the reason why we sit here is that we have also developed innovations together with partners, how to recirculate nutrients, such as both phosphorus and nitrogen, and into new products, and to be able to serve a future circular food system. Today's session will 100% focus on, in this case, the AQUAPHOENIX project. It's an EU project that have more than 20 different stakeholders that in together can create this full circle that we'll come back to. And we will listen to Dr. Hans Klevdal from Norse later on explaining the AQUAPHOENIX project. But it consists of one fjord in Norway when we do experiments, but also the Baltic Sea in the form of fish farmers from Åland. My company's interest when it comes to this matter is, of course, based on that we are a waste management company, and we originate from 1881. But we started to get requests in our operation when we caught dead fishes and transported to biogas plant to also collect fish sludge. And the reason was, of course, that there were a problem to getting environmental permits. We can see that since the last 10 years that this has expanded, so it's even more problematic now going forward. And we set up our first systems in 2020. The first systems and the first start was also supported by the Nordic Innovation that is part of the Nordic Ministers' Council. So with the great support of Nordic countries, we could start to develop these innovations. Our first international outlook we did in COP27, where we together with a Chilean-based fish company, fish producer, did a broadcast about the potential in fish farming. But we saw exactly the same problem as in Norway, that eutrophication causes this problem to then having more licenses for fish farming, and then we understood that this is a global problem. And we also saw the direct connection between climate and fish farming, and how circular solutions can avoid huge amount of emissions. So COP27 was the starting point in Sharm el-Sheikh for our work. We also presented our work at COP28, and then we had been more firm what we wanted to do. And we also had the honor there to have Professor Malo Barange to do the keynote introduction. He will also do the keynote introduction very soon about what is needed when it comes to food production in the aquaculture going forward. The ambition that we presented in COP28 also led to more development and more understanding that this is a very complex area that need to have many stakeholders. And of course, one of the big risks when it comes to mitigate the increased production is the feed that we give the fishes, and how to make sure that we then can bring them back is important. And the big issue is, of course, the eutrophication. So I'm very glad that we will have the latest science from in this case, Dr. Vivi Fleming from the Finnish Environment Institute Psyche, also explaining about her research in the Baltic Sea. And what we know for sure is that circular solutions are very hard to develop by yourself. You need to have the full value chain with you. So therefore, we applied together with Norse, together with these other 20 stakeholders, to this AQUAPHOENIX project. And we were granted this in 2025. And Hans Klevdal, as I mentioned, will deep dive into the project, how far we have reached now, and what the ambitions are for the future. But when it comes to the closing the loop, this was the starting point when we applied for the AQUAPHOENIX project to really make sure that we utilize the value. And the secret ingredient also be able to supply and pay for a lot of the system is the value of the phosphorus. The phosphorus if it goes into the fjord or into the ocean, creates eutrophication. But if you can recirculate the phosphorus, then suddenly we have another ball game. We also at COP30 continued to have these dialogues. We also had, in this case, IKEA that also showed their interest to have more sustainable fish farming. And also we understood even more than the importance when it comes to the planetary boundaries, and that fish farming as such, if we can create it circular, will reduce the risk of overshooting several of the boundaries. And what also have stressed the importance is, of course, the problem to get new environmental permits. But again, the phosphorus are a key element. I would like to just before I end and introduce the other speakers, show a little film and then have an end picture. And this is how we are now working to develop the phosphorus product and how we can do that. And I will have shared this separately with you, so it will come. Here we have it. We make sure that we do it in the right way. Verify that you hear the sound as well. So this is what we are doing when it comes to the development of collecting, in this case, phosphorus from the system. As I have presented, we do have a big challenge, and that is legislation. So the blocker to do this can be that if we can use the phosphorus, it will be too high cost for the society and too high cost for the fish farmers. But on the contrary, if we can use the phosphorus, the value of the phosphorus could almost pay for the system to collect the fish sludge. Just an end picture. What we see now, what is happening, is that environmental permits are revoked. I visited, in this case, Canada here now for the last 2 weeks, and the last meeting was with was the Ministry of Fisheries in Canada, and they have reduced their environmental permits with more than 40%. And this, of course, creates job losses. Here we have the First Nation that are very involved in the fish farming in Canada. The same happens now in Norway, and a small part of the fjord has now revoked to sales value of more than 1.1 billion euros. So the potential is huge. Okay, with this, I'd like to introduce our first keynote speaker, and I'm really happy to introduce Professor Manuel Barange from FAO. You are the Assistant Director General, but you also are responsible for fish farming for the aquaculture. And as I said in the beginning, I was really happy to have you also to do the introduction at COP28. We have now developed it even further. So, of course, and we would like to hear your view, what is happening and what is needed going forward. So please, Professor Barange, the word is yours.
Thank you very much, Par. I'm just going to share my screen as I have a presentation to show you, and let me see if I can succeed. And if you can confirm that you can see the slides, then I can proceed. First of all, to tell you that the things that I'm going to mention today, the framework that I'm going to provide to you to the discussions, come from the SOFIA report, the State of Fisheries and Aquaculture report, which is known to, I guess, most of you. And the latest edition was actually released in Kenya last week. So I've just come back from Mombasa, and if you want to know more of the details, there's a QR code on the screen that you can use to access the report. Now, what I'm going to do is just give you some of the flavors of what the directions of travel we are in the area of aquatic food systems, and hopefully it will be a good introduction to the discussion that follows. So first, to tell you that the aquatic food systems, aquatic production continues to grow. It's an all-time high. And you can see the enormous transformation that has taken place, in fact, over the last 35 years, with capture fisheries in blue stabilizing to around 92 million tons in the last assessment, but then having aquaculture exploding, really. If you look at animal aquaculture, it has passed now the barrier of 100 million tons of aquatic animal production in 2024, in addition to about 40 million tons of production of algae. As you can see as well by the colors in the figure, that marine aquaculture is actually not the majority of aquaculture. Inland aquaculture is a much bigger production unit. Also to mention that in terms of the biodiversity of the system, that it is remarkable that we have almost 800 species that we farm in aquaculture. This is an enormous biodiversity compared to any other food production system on Earth, and almost 4,000 species that we capture. And as you can see, marine fishes are mostly captured, freshwater fishes are mostly farmed. Now, how we translate that into food for all of us. Again, in 2024, the latest year that we have full information around the world, we have a new record, 174 million tons of aquatic animals. I'm referring now to animals only, produced directly for human consumption. There's, as you can see in the figure in orange, about just under 20 million tons of fish that, or aquatic production, animal production that is not used directly for human consumption. It is used mostly for aquaculture feeds, other animal feeds, nutritional supplements, pet foods, and so on. But you can see how the industry is becoming more efficient because the volume that is not used directly for human consumption is being, in fact, reducing over time, both in volume and in percentage. And in terms of per capita, what we have in this dotted line that you can see here is that the current availability, per capita availability, is around 21 kilos, 21.3 to be precise, which is more than double the availability when I was born. So in one single generation, we have more than double the availability. And that is making some significant contributions to nutritional improvements around the world. You can see the global average, 21.3 kilograms, almost 100% growth since 1970. Now, of course, aquaculture is the main driver of this growth by far, because capture fisheries, in fact, has been stabilized, and it should be stabilized and should not be growing because it relies completely on the vagaries of nature. Now, this growth is very diverse, geographically diverse. As you can see on the left, almost 90% of the aquatic animal production comes from Asia. But if you look in the middle panel, the growth rate over the last 24 years, you can see that while globally it has been growing at almost 5% per year, which is a very significant growth rate, by the way. You have regions like Africa and Latin America that have a very small production overall, but that they've been growing at above the global average in the last 24 years. Note as well how the European Union area, the EU27 area, in fact, is the only region in the world where aquaculture is not growing. Perhaps North America as well, you can say that this is stable, it's not growing either. There are particular reasons, and Par, you mentioned some of those. There are others, and it's just important to note. Now, one thing that is very important is that if you look at the red line and the blue line in this figure, the volume of fed aquaculture in red has been growing faster than the volume of non-fed aquaculture. That's animal aquaculture, of course. So the fed aquaculture is now approaching 75 million tons. But we should actually be really happy that the volume of marine fisheries used for fish meal production, in fact, has not increased. It's much lower than it was in the 1990s, in the early 1990s. In other words, that this increase in production is not connected to an increased requirement of feed from the ocean. This is one of the questions that we are asked about more often. Are we, through aquaculture, depleting the ocean more? No, that's not the case. This is at the global level. Of course, there are specific pockets, geographic pockets, where the trends may be different and maybe question whether the industry is operating properly or not. But at the global level, there is no connection between those two. At the same time, one of the reasons for this continuous growth without requiring more fish meal production, or rather capture fish that is used for fish meal production, is the use of byproducts, and is very connected to what the topic of this seminar is about. Over 30% of the fish meal production and over 50% of the fish oil production now comes from byproducts. The skins, the bones, the heads, in places where those are not used for direct consumption. And again, this is an indication of an industry that is becoming more efficient and it takes more care into the resources that it uses. But more is expected from aquatic food systems in coming decades, of course, partially because we're going to be almost 10 billion people and we all have a right to food. And, everyone likes to eat preferably 3 meals a day. And so we need to make sure that there is enough food for everybody. Now, FAO does a number of projections. We have a sort of what we call medium-term projections, 10-year ahead projections, and then longer-term projections. These are the results of the medium-term projections for the next decade, based on a full bioeconomic model of all food commodities. So in other words, there's elasticities into terrestrials and aquatic foods in it. And on the basis of this model, what we see is by 2034, so for a decade of projection, we expect aquatic animal production to grow to about 214 million tons. That's about 10% more than in 2024, so a 1% growth per year, of which almost 60% will come from aquaculture. And as you can see, the growth for the different subsectors, capture fisheries, very little growth in this decade, 3%, mostly about management effectiveness and also reduction of loss and waste, while aquaculture growing 19% in that decade. This is a very conservative, in fact, projection because it is based on, as I said, full connection with all other food production systems. And very often, these estimates tend to be a little bit underestimating what might happen in the industry, but it's a good baseline to look at. Now, if this is confirmed in a decade from now, the consumption, the availability of aquatic animal foods for each one of us will be just under 22 kilograms, which is a moderate growth. but a moderate growth that comes at the same time as a significant growth in population. So in fact, it is a net contribution to improvements in nutrition to all of us. Now, it's important also to note that the per capita availability will grow, in fact, everywhere, with two exceptions. Europe, which is marginally down, almost within the margin of error, so I don't make much of it. But in Africa, in particular, sub-Saharan Africa, we do not expect this increase because this production growth will not keep up with population growth. In fact, if I look at this per capita availability year by year during the projection period, you can see, in fact, this decrease year on year in the availability of aquatic foods in Africa to go just almost below 9 kilograms per person per year. Look at that by the mid-2010, we were already over 10 kilograms per person per year. So that's already 1 kilogram, a 10% reduction, just because the production is not keeping up with population growth. And this has to focus people's minds. It certainly focuses FAO's minds because we need to make sure that we respond to this reality. So now let's look at a bit further ahead, not just a decade ahead, but to 2050. And this is just a scenario analysis of, let's assume that the actual availability of aquatic animal foods that we have in 2023 is projected into the future. So how much more production do we need to keep the global consumption or the global availability, depending on how you want to look at it, at just under 21 kilograms per person per year? In Africa, less than that, at just 9.1 kilograms per person per year. If we just were to keep that consumption as it is in 2023 into 2050, globally, the sector needs to grow by 19% in the 20-odd years that we have left. But if you look at Africa, that growth is approaching 70%. This is a very significant growth, and this is only to keep the availability of aquatic foods in Africa to the level currently of 9.1 kilograms, which is already half of the global average. If you wanted to increase Africa's availability to the global average, this 67% will actually become 270%. So it's a very significant push for the sector to grow in particular regions. And it is for this reason that FAO developed the Blue Transformation Agenda, an agenda that, again, there's a QR code there if people want to get access to the document, which has now been supported in the G7 and into G20 as a priority, because the aquatic food system is one of the very few food systems that is demonstrating significant capacity to further growth. And this transformation agenda has three very clear objectives, which I will not go into the details, but just to sort of break them up for you. The first one is to ensure that aquaculture, sustainable aquaculture, continues to satisfy the global demand for aquatic foods. It's the only subsector that can provide that growth. It will not be from capture fisheries. And I'm pleased also to say that a year and a half ago, FAO managed to negotiate with all countries new guidelines for sustainable aquaculture, which provide guidance to all countries as to how to develop the sector. And that includes circular economy issues, issues of feed, issues of environmental protection, and so on. So all relevant to the seminar today. The second objective is to ensure that all fisheries are placed under management. The latest assessment of FAO is that around 37% of all global fisheries are overfished. That doesn't mean that they're disappearing. It doesn't mean that they are becoming extinct. People confuse terms. It means that if you use a banking equivalent, you are extracting from your bank account more than the interest that the bank gives you, nature's bank. And so you are slowly reducing the capital in your bank account in the wild populations in the field. We know that management works, but it has to be implemented, and there's still many fisheries that are not under effective management. And the third leg of that stool, of the transformation stool, is the development of the value chains of aquatic foods. So it's not just about production, it's how do you reduce loss and waste? How do you add value to the product? How do you facilitate access to the markets? The trade, by the way, of aquatic products nowadays is in value pretty much the same as the value of all land meats together. So it's a very significant trade value. And we need to facilitate that further so that the consumer gets access to this top production, top protein and top micronutrients. This is what we are selling around the world. This is the basis of every intervention that FAO has around the world. And it is supported by all the countries of FAO, the members of FAO, which have agreed to this agenda. Finally, if we were to implement the blue transformation as we have defined it in the agenda, we have already projected that by 2050, by the middle of the century, we could actually increase the availability. Sometimes we call it consumption, but it is apparent consumption, is the availability of aquatic animal foods to each one of us around the world to over 25 kilograms. This is a significant growth from currently, and the 20.1 in 2020 is now 21.3 in 2024. Most of that comes from, as you see in blue, from aquaculture, more than 60% coming from aquaculture. So aquaculture clearly is the focus. It is the target of most countries that come to FAO requesting support, and we need to find solutions that work, that tick all the boxes, not just the production boxes, but also the environmental boxes and the economic boxes. So with that, thank you very much for your attention. I hope this is useful for the rest of the seminar. And of course, I will be connected for most of the seminar for any questions. Thank you very much, Pa. Over to you.
Thank you so much, Professor Barange. Yes, Europe are declining when it comes to production, but increasing when it comes to import of aquaculture produced fish from other parts of the world. So Europe are competing with the rest of the world. So if Europe then could boost the production, that will also help the total consumption. With this, I would like to introduce Dr. Vivi Fleming, with a background in marine ecology and focus on science when it comes to the decision-making and policies. She has especially focused on eutrophication in the Baltic Sea. And she also are part of both on regional and on EU level when it comes to the facts that when it comes to evidence, what is possible and what are the threats. Your work are interdisciplinary, and you do collaborate both with engineers, political scientists, economists, and educationists, as well as colleagues that you work with in different fields when it comes to natural science. So really look forward, Vivi, to hear and listen to your findings when it comes to the risk of eutrophication. So again, the word is now yours to present.
Thank you, Per. I hope you can hear me. And thank you very much, Manuel, for the interesting first keynote speech. Without any further, I'll share my presentation. I hope you see my presentation. Can you, Per, just confirm that you see my first slide?
Yes, we do, and it's full screen, so perfect.
Yes. So as Per mentioned and introduced me, I'll be talking about eutrophication and then going a little bit in more depth into the case of the Baltic Sea, which is the one I know best about. I'll be talking, or the questions I'll be touching is eutrophication, just in general. What are we talking about when we talk about eutrophication? The case of the Baltic Sea, why that case? Then is dilution the solution to pollution, which is one of those old sayings from the past, and I'm asking how or whether it's possible to turn to reverse. And then what we're talking about in this seminar is food production. This is not my field of expertise, but I'll try to connect, give an example. So eutrophicated is actually from the Greek language, which means well-fed. That's a very loose translation. Broadly speaking, we're referring to increase in the production or organic supply or nutritional state of an ecosystem. And this is usually caused by nutrient enrichment. There are, of course, many different ways of expressing this, but that is the most broad one. Often, but not always, this, eutrophication, which is a process, it's anthropogenic, so it's caused by human actions. In some cases, in the worst cases, it becomes excessive and disturbs the environment. In the marine environment, it may manifest as increase in algae biomass, opportunistic species, general decrease in biodiversity. It may increase the particles in the water column, increase turbidity, and decrease water clarity. As an indirect effect, it may cause near-bottom oxygen deficiency and dead bottoms. And what we often see is massive algal bloom events as a result or as part of eutrophication. Chlorophyll A is the pigment in the phytoplankton, in the planktonic algae in the water column that is expressing, in a way, the amount of algae biomass in the water column. It's used as it is the most descriptive indicator of eutrophication and most widely used as to indicate eutrophication. This is a picture of the Northern Hemisphere summertime from satellite images showing areas with high phytoplankton production through chlorophyll A. And we can see that there are some areas with high production in the Northern Hemisphere in general. There are some areas which are high due to upwelling of nutrient-rich water, but especially you can see that coastal areas may be highly eutrophied, and that is what this high amount of chlorophyll A in the coastal areas is expressing. Just arrowing out our little Baltic Sea and the color of it in this map. Trends in chlorophyll A, or the amount of planktonic algae in the water column, are increasing globally. And we can see this increase in the Northern Hemisphere, but also the Southern Hemisphere. And when we zoom into the Baltic Sea, our case in this talk, definitely the chlorophyll A has been increasing there. And from this figure, you can see the increase since the 1980s, which was already a peak eutrophication time. And the little green line is showing a scientifically based estimate of what would be the good status. So we are clearly having much more algae in the water than what a good status would imply. Well, a few words of the Baltic Sea, just quickly, to introduce it to those of you who are not acquainted. It's a semi-enclosed brackish water basin with 9 coastal countries around. It's very shallow with an average depth of a little over 50 meters. It has a large catchment area, which is highly populated and has a lot of freshwater input and nutrient inputs also already naturally. And due to this semi-enclosed nature, it has a very slow water exchange of 30 years turnover time. So it's very prone to eutrophication. Besides chlorophyll A, another example of how the eutrophication manifests in the sea is deep bottom oxygen deficiency, which is actually already covering most of the deep bottoms at the moment. And it's extending to the coastal areas, which doesn't really show from this robust visualization map. There's a severe eutrophication in the area throughout in this map and also in this table. The green colored are the areas with good status, or the indicators with good status. So this area originally was what is called oligotrophic, meaning that it was nutrient poor, but it has become very eutrophied, and a lot of it is due to anthropogenic, long-term anthropogenic inputs. We know a lot about the eutrophication. It's assessed with many different indicators besides chlorophyll A. And what I want you to notice also from this picture is that the open sea areas of the basin are even more eutrophied than most of the coastal areas. So the basin is eutrophied throughout. Well, what is the actual process of eutrophication in this sea and in many others? We call it even a vicious cycle. And I'm showing this because it actually explains why putting on the reverse gear or going backward trends is so slow. So nutrient loading increases the nutrient in the water, which in turn increases the phytoplankton in the water, the algae, and it descends into the bottom as dead material, causing oxygen decomposition and bottom oxygen deficiency. This in turn may release phosphorus that is bound in the bottom sediments into the water and increases again the phosphorus amount in the water column. Massive algal blooms in the Baltic may utilize this excess phosphorus, and we have bloom events of cyanobacteria that again descend as dead matter in the bottom and then accelerate this whole circle, increasing also the nitrogen in the water column. And then the outcomes are, which I mentioned earlier. And not to make this easier, the climate change will be just accelerating the process. After the water temperatures rise, also these planktic algae and massive blooms increase. So this is what causes also difficulty in turning backwards in time. Well, we have the good news. Overall nutrient inputs into the entire Baltic are approaching reverse gear. When it comes to nitrogen, they are already below the so-called input ceiling, which has been agreed together to represent the target for the sea, and phosphorus is approaching that level. But looking into the nutrient concentrations in the seawater, they are not yet decreasing. The red line shows the actual development of phosphorus in the sea. Sorry, the writing is not correct. It's not inputs, but the amount of phosphorus in the sea. It has started to level out but the yellow line shows what it would look like if the restrictions had not been made. So we are really able to make a change, but to be able to actually turn to reverse, to go back in time, that needs more. The nutrient inputs into the Baltic Sea, and this probably is the same in many other eutrophied areas, come from different sources. The biggest source in this area is diffuse, meaning agriculture mainly, also forestry, that is the orange sector. And then for phosphorus, point sources are the next highest, and for nitrogen, the atmospheric deposition. But this may vary between different areas. When we zoom in to, for example, the Archipelago Sea area where this AQUAPHOENIX case area also is, we can see such figures. The agriculture is by far the main component, but there's also a sector for point sources, and this is where fish farming would be. I want you to also notice here the sectors that are high concerning natural load. This is something that we can really not affect, and that is also slowing down whatever measures we take. The natural load will still remain. Looking at these pies, it looks like the point sources would not be such a significant sector. But if we zoom in even more locally, then they might make a much bigger difference. Taking an example into fish farms, I just want to remind that the loading from fish farms may come through two ways. There's the sludge mentioned earlier, meaning organic matter that deposits into the bottom, causing oxygen deficiency, and what we call internal nutrient loading of phosphorus, and again, then algal growth. But in addition to that, there's inputs of dissolved inorganic nutrients directly into the water from the fish farms. And this would be called more like direct loading. In Syke, my colleagues have been using the coastal model FICOS to simulate the effect of fish farms through excluding the input of fish farms from simulations and comparing that to the actual loading. And looking into this very zoomed in map of the archipelago, you can see that removing fish farms actually cause a change in chlorophyll A in these very local areas, and putting in where the fish farms exist just to show that this is the exact areas where that would happen. They also simulated the same with the indirect organic, the sludge loading, and received similar, not exactly the same places, but similar local effects. Okay, I'm coming towards the end of the presentation and giving you some take-home messages here. Firstly, eutrophication is increasing worldwide, and many coastal areas are severely eutrophied. And most of the nutrient loading, both in the Baltic Sea, but globally as well, is related to food production. And then some of my questions. I think I could show here that dilution is not the solution to pollution, just through the Baltic Sea case. It has been underloading for a long time, and the open sea areas are affected and very eutrophied, more eutrophied in some cases through our measurement, our assessments, than the coastal areas. And actual simulations have shown that there is a pressure on the coastal areas, both from the open sea and from the coast. So actually we're turning to an opposite direction, that the open seas may in a way eutrophie the coastal areas as well. And the second, reversing takes as least as long as creating the problem itself. Thank you.
Thank you so much, Dr. Fleming. My conclusion directly is that from Mano Barrage, we need to increase our food production, but you're saying that we are threatened. There are big problems going ahead if we're going to increase it, because eutrophication might stop the potential to produce in the aquaculture. So of course, this is troublesome. With that, I'd like to introduce Dr. Hans Klevdahl. You're Head of Market and Innovation for NORCE, Norwegian Research Organization. You are a leader with experience both in research, innovation, and business development. And that's very rare to have this combination, to understand both business science, but also innovation and policies. So, of course, you have spent your career in bridging between those different areas. Now you're leading the market innovation for a Norwegian Research Organization, and you are also the leader when it comes to the AQUAPHOENIX project. So please take the floor and present the AQUAPHOENIX project and where are we right now and what is waiting around the corner.
Thank you, Per, and good afternoon, everyone. Thank you to UNEP and to all co-organizers for being able to have this webinar. I'm going to start with an in-flight video from our project to give a flavor of where we're coming from. Do you see some pictures on that I'm sharing? No, let me see. I do like this then.
Now we see something coming. Yes.
Great. So I'll start with a short video.
Aquaculture has a huge weight on its shoulders. It's expected to provide more and more food for a growing population, but at the same time, we're facing challenges in terms of the environmental impacts of a growing sector.
The people who engage and are involved in this sector are people with a vision for the future, who are adaptive, creative, and very much solutions-oriented.
AQUAPHOENIX is a project funded by the European Union to advance sustainability in aquaculture.
AQUAPHOENIX is a circular project, but it's a circle with two important halves that fit together. We have, on one hand, sludge collection, collecting the sludge from aquaculture activities and reducing the environmental impact.
We do expect that if we quantitatively remove sludge from the system, that we will get an improvement of the benthic habitat situation, more diverse community, for example, also of the larger organisms that live there.
On the other hand, we have the use of that sludge into a number of valorization streams, creating a number of useful products for consumers in Norway, in Åland, and throughout Europe. It's a portable, transferable, and scalable solution.
Mission Restore Our Oceans and Fresh Water is looking at strategic objectives across the European Union. There is a commitment to promoting low impact, zero carbon, and circular aquaculture. The AQUAPHOENIX project directly contributes to those three areas.
I'm happy to be involved in a project that is designed to make change, to drive an improvement in industry in order to make a better and sustainable use of these really beautiful ecosystems.
And I think that's what we're all here for, to make use of these beautiful ecosystems in a sustainable way. So my name is Hans Klevdahl. I'm with NORCE. I'm not the coordinator of the project, but I'm heading this activity in NORCE. I'm really glad for the introduction from Manuel and Vivi, and thank you for this very nice presentation of the Sophia report. I will not echo or repeat your messages, Manuel, but I think that some of the points you pulled forward is very interesting to our project AQUAPHOENIX, especially that the fed systems are growing, that the marine and coastal production systems are amounting to about 40%. And that means that the growth will probably also happen in the fed systems. Even though the aquaculture is rapidly industrializing and being very central to global food security, the bottleneck will be feed and sustainable feed and access to sustainable sources of feed. And the other thing that will be a limitation is coastal and healthy and productive zones for production. So this is about, as we saw from Vivi, about regenerating burdened coastal zones to make sure that they are productive and can support that food production that's needed, as we heard from Manuel. The key constraints is therefore shifting from volume to sustainability. So feed, environmental impact, and climate resilience. In Norway, that's our sort of home ground. That's an industry that's been going on for 50 years or so. As you can see, 1.5 million tons of salmon and trout. And as you correctly pointed out, Manuel, we are not growing. The volumes are not growing for several reasons. But one of them is that the load on our ecosystems, load on our fjords, and also biosecurity, salmon lice, which is a parasite that is challenging to the industry. The production systems is for salmon is open pens. It's also closed systems that are starting to be established, and also land-based systems. So this is a strictly managed and regulated industry, and argued to be one of the most sustainable complex animal protein produced. As you can see in these rings, in one of these rings, there are the same amount of meat as a cattle herd of 2,000 cattle of 500 kilos in one of these rings. It's very area intensive, but again, you can imagine also what it looks like after such a herd. If the offals and the sludge goes directly into the fjord, it looks like this. Capturing and recovering the sludge, which is the offal from feces from the fish and also uneaten feed, is something that needs to be done. But looking at the tests that are done, we see that this continuous emission of sludge, as you can see here in the lower right, that has been going on for 50 years. So you can imagine how the fjords look like. In some areas there is a great shift of water, so the problem is not significant. But there's been a lot of awareness around this. Some of our fjords are threshold fjords, so there is not a good shift of water. And this is, of course, with the climate change becoming, the water is coming warmer, and the shift is being poorer. This is the situation in Norway, and this is where we sort of is the birthplace of the project AQUAPHOENIX. But of course, as Vivi also showed from the Baltic Sea, this is also an area that we collaborate with in the project, and that has some of the same challenges. So together with Finnish researchers, companies that wants to look into solutions, we developed this project, AQUAPHOENIX. It's a Horizon Europe funded project under the zero emission ambition for 2040, and it's over 4 years, 18 partners, will collaborate mainly with between sites in Norway and in Finland, close to where some of the sites that mainly Vivian pointed to. So we have a great consortium, and I think that the partnership is definitely an important part. Making circular economy work doesn't always require just technology. It requires the partnership and the engagement. So I think this is not only a system demonstrator for technologies and system integration, but also for enduring partnerships. What we face is when we have drawn our vision, a fully closed loop. We take the Norwegian aquaculture as an example, but in a CO2 footprint emission of about 7 million tons equivalents per year. The challenge to the aquaculture industry when it comes to salmon, and with some parallels, I would say, to both shrimp and tilapia and other species, is what goes in and what goes out. So it's the footprint of the Norwegian salmon, in our case, is 80% of made by the feed because of the imports, 92% imported. And the sludge that is going directly into the fjord bed conventionally is also making an environmental footprint that I already pointed to. Now, this is moving not only biomass from the soy fields in Brazil up to the fjords in Norway and leaving it on the fjord bed, but it's also taking important nutrients like Per alluded to, phosphorus from mines in Morocco to Brazil to grow the soy and then take it to Norwegian and Finnish fjords and leave it in the fjord bed. So this is a waste of resources, and that's why our mission is really to look forward and see how we can use the right-hand side here, the right-hand problem, to solve the left-hand problem. And that's by first by recovering, by processing and reusing the nutrients. The mission is really to enable a responsible growth of fed aquaculture through circular resource flows, and that is to mobilize resources that has not been conventionally used in feed production or fertilizer production to make the soy into an asset and into an important input factor. So aquaculture has had great success, as we've seen, but it has the backsides, and in order to grow responsibly, it must grow in a different way. And that is why by addressing the challenges. So capturing and storing the waste, validating the conversion of sludge into assets, and reducing emission, and restoring the production zones that we are already established in. The system innovation for new value chains that we are now demonstrating is about demonstrating and establishing these collection systems that are under the open cages here. So we have a work package on that. So that's working together with the commercial companies, like companies that also come from the oil and gas industry, engaging into aquaculture. We are also looking at the effect of sludge removal from the seafloor. So see how over years how the sludge removal will have an effect on the benthic ecosystems. We will also do the same thing on the pelagic ecosystem. So in the water phase, see how it can affect the life there. And then it's about getting the sludge to land and valorizing the resources by filtration, removing the water, keeping the sludge stored safely, and then transport it to land facilities and start developing bioenergy and nutrient recovery from those sludge streams. So it's about it's also about enabling this scale. It's not only about technology, as I said, about collaboration and how well we can work together, but it's about enabling this industry to scale the systems and solutions by novel governance and policy innovation. There are several regulations that are unintendedly a barrier to the reuse of nutrients, and particularly in the EU regulation area. This is being pushed and worked well with. There are a lot of ambitions and strategies that are being put into place that will push this in the right direction. Also the Circular Economy Act, the Marine Strategy Framework Directive, and of course also the Critical Raw Materials Act, where phosphorus is listed as a critical raw material. So this is really the AQUAPHOENIX in a nutshell. It's about really putting the circularity into a system. But the right half here will not drive this activity alone. We need to develop a market. We need to develop a market pull. We need to show that the value of the nutrients that are now lost in the bottom of fjords, that has a value, and that has an importance also for the food systems and also in many areas. It should not be a compliance-driven process alone. We must do through value creation. So this is how it can look. This is a sludge collection system in Norway, in the Hardangerfjord. This is also an area where there's a controversy around how the sludge is affecting the fjords, how it's affecting the local fishing, the life on the sea bed, and with several other species there being affected. And we had a meeting just some weeks ago at Åland, and the first site is also being established there in full scale. It's important to do this in full scale, in commercial scale, several sites over a long time period, over years, in order to evaluate the robustness and the effects on the environment. So in 2029, we will hopefully see that our objectives are giving impact, or that we will be in position to demonstrate the potential to have an impact. This is our core. This is our lighthouse of what we are doing, to have our objectives and our activities to give results, to be a global demonstrator of circular aquaculture and circular resource use. So fish sludge is not a waste problem. It's a resource stream waiting for the right system. And with that, I thank you for your attention, and you can also check out our website that will be available after the meeting. Thank you.
Thank you so much, Hans, and we make sure that the slides are available. I know, Professor Barange, you need to leave. It's at 3:15. So with that, before we ask Christine to present, your reflections so far when you hear about what Vivi has presented and what Hans has presented. Professor Barange?
Apologies, Par. I didn't think that was for me. I see that Vivi still has screen shared, so
Oh, wow.
perhaps,
Vivi, can you stop sharing screen from your side? Sorry, I don't see that from my side. So
I don't see it from my side either, because I tried to share again.
Now seems to be gone since I've got I had your anyway. Thank you, Part, for giving me the floor. Given that I need to leave, and I think that this is a very, very good seminar. I really appreciated the presentations. I think that the problem has been very well explained. Luckily, the situation of the Baltic Sea is not something that we have in other areas. The Baltic Sea has a very significant problem of eutrophication, and from the presentation, in fact, of Vivi, it's very clear that the majority of the problem is actually agriculture sludge. So we are focusing here on aquaculture, but really we have to do something about the release of nutrients from agriculture, which is really the fundamental problem here. But I think that the industry, the aquaculture industry, has already demonstrated an amazing capacity for adaptation and evolution. The fact that in salmon now you can have 1-to-1 1 kilo feed for 1 kilo production, virtually using mostly vegetable meals as opposed to fish meal. When 20 years ago it was 4 kilos of feed for 1 kilo of production. So this is amazing, and I think that the industry should actually be commended for it, and there should be more discussions in the press as to the value of that production, bearing in mind as well that the efficiency of aquatic food production it's much higher than the efficiency of chicken or pigs, or of course beef, in terms of feed to flesh ratio. So this aquaculture is clearly a solution, but finding solutions that also minimize that environmental impact in the case of mariculture are important. Of course, the majority of the aquaculture in the world is actually on land, is on the base of ponds that could be cleaned as they are, that could be nutrients can be removed as they are, and the problem is limited. But when it comes to aquaculture in lakes, in the sea, removing the sludge is very important. Making circular economy solutions is very important, and I think that what you presented here shows really a way forward. So thank you very much for that.
Thank you so much, Professor Barange, and stay as long as you can, because the next presentation will be amazing when it comes to new technology in fish farming. And I totally agree with you. Now the fish farms are paying the price of bad nutrient management in the agriculture. And of course, we can't blame. We need to make sure that we do at utmost in both parties. With this, I'd like to introduce Mrs. Christine Dahlgren. You are the project leading coordinator who's with Watermoon, and you have also a Master of Science in Aquaculture and passionate about driving innovation and development in the aquaculture. So please give us your passion and also the innovations, Christine. The floor is yours.
Thank you, Par, for that great introduction. I think first I will need a bit of help sharing a video from Vanjiro, if you have it. And then I don't think I'm going to say much before the video is done.
Norwegian aquaculture stands at a crossroad. High ambitions, driven by a vision of growth and sustainability. Imagine the possibilities if we could unlock the potential of the fjord and seas. So we set out on a journey. We searched for solutions, seeking innovative technologies that could redefine our industry. but none could fulfill all our aspirations. Undeterred, we decided to forge our own path. For years, we have poured our hearts and minds into developing a groundbreaking production platform. A system that raises fish from their earliest stages to full maturity, free from the scourge of lice. A system that captures waste, preserving the purity of our oceans. A new era of sustainable aquaculture is on the horizon. Water Moon.
Thank you. And then I hope everyone can see the full screen. Now it's only black, but from now, can you see a full screen?
Yes.
Okay, perfect. What I'm starting off with after this short introduction video is I'm gonna take you through what is Watermoon, how did Watermoon become, and what has this to do with circular aquaculture. So first, just to get things started, we have to start at the beginning of how AIDA, which is the family-owned business that owns and started Watermoon. And they have now the third generation, so it already started in 1970 with the small farming of salmon and trout in local water in close to the Hardangerfjord. And then further, the second generation expanded the company for sea-based aquaculture with salmon and with trout. And then now we have the third generations, Sondre and Erland, which takes the lead into the future of aquaculture and have started different and new solutions for further future. So I'm not going to dig deep into the global food shortage as my former presenter have presented that very well, but that is the main part of why we need to see what can we do different in aquaculture. We need more food, and how are we going to do it in a sustainable way, both according to the challenges with sea lice, escapees, and also the local footprint and sludge that have been an issue on some sites and in some fjords, as you've already seen. So what did AIDA do? AIDA went out and searched in the supplier market for new technology and solutions that could improve aquaculture challenges, as I mentioned, to produce more food in a sustainable way and being able to expand. However, the solution the market had, or the solutions, had not yet become at the level that AIDA was searching. It had to check all the boxes on collection and sea lice protection, and also be sustainable and manageable. So when they didn't find what they were searching for in the supplier market, AIDA looked into themselves as a family business that been now 55 years of experience with aquaculture from start to now having multiple locations of production. They saw that they had the knowledge inside the own company of biology and operations, and what the only thing they missed was how do we build it? So what they did was they combined engineering knowledge and biology and operation knowledge to now design and draw and produce a solution for themselves. And it started naturally as other developers. The natural step is starting in small scale and then going up further into full scale and full production, as IDA did the same, and also making sure the requirements were built both to requirements of authorities, but also the requirements of the big boss, which is the fish, of course. So they started in small scale, and that's about 30 cubic. So this unit, as you can see, if I can point here, this is about 7 meters tall and 3 meters wide. So they started and quickly learned the technical parts that worked. And when they knew that the technical part of the unit worked, they quickly set fish inside of it to test how does the fish react to a closed containment environment, because that's what this is. It's a closed containment. And when they had the first production cycle, they went from smolt to harvest in 11 months and saw that this is something that we can work with. And many of you will think that the next step will be maybe enlarge a bit more or do some more tests, but IDA found out that if we're going to know if this works, we have to go large scale or full scale production. So that is what IDA did after the first production. They went from small scale to full scale production. And as I'm sure you're aware of, it's not just to enlarge everything you have designed and engineered. You have to make many adjustments, you have to have a certification, and further on going into the fabrication and commissioning of the unit, where IDA was entering a new field as an aquaculture business. All the engineers and all the biologists and fish health experts had to contribute during the fabrication to make sure this unit was built up to the standard from the most important part, the fish, and also the sludge collection, of course. Further moving on to installation, transportation, and test and startup. And then a year later, after starting production of the unit, they could gladly put out 197,000 smolts in this 30,000 cubic unit. So this is the first production they had, and now we're on our third production. And now the real test begins with operating the unit and learning from the unit and constantly focusing on learning and getting better on how to use this whole new way of producing fish. So let's get into some technical details of how this works. Not going into very detail, but let's keep it to an overhead part. So Watermoon has a closed barrier, entirely closed. It's not semi-closed, it's closed, with a membrane on the outside and two steel parts at the top and at the bottom, where the top part works as a buoyancy and the bottom parts collect sludge, dead fish, and whatever, and also circulates out the water. And the water stream comes in from two parts with a pump at the bottom, pumping water into a water tower. And then we have the water pumped into the unit in a circular, uniform water quantity. So the technical producement capacity of it is 1,500 tons with a 30,000 cubic volume. And because we have a closed barrier and the water inlet is at 50 to 70 meters, I will come back to why, we have had zero lice and zero need for any treatment of the fish. And while some solutions are based on making big and heavy solutions to make sure that the unit can withstand harsh weather, Watermoon has a more flexible material, as this material is made out of a tarpaulin or a membrane, which also gives it a whole new technical use for when we have bad weather, which we often can get in Norway and the West Coast. We lower the unit down 20 meters. This solutions for lowering it down 20 meters is for removing the unit from the big waves and forces so that Watermoon can endure more harsh weather for a longer time. And also, one of the most important parts of the Watermoon is the collection of particular waste. So the particular waste or sludge is collected at the bottom of the Watermoon unit, and the waste sinks down at the bottom where it's collected, and it sinks down with gravity, and then it gets sucked up and pumped out from the middle of the unit and up and out until the fleet, where it will be picked up and it will be treated a bit on the fleet. And then Hans described the rest of the part where the sludge get treated and used for example, biogas or many other parts. So this means that we treat a partial part of the water stream, and I will get back to the results after. On our second production, which we have now completed. So we're now on our third production cycle, but it's not yet completed, so we don't have the full results yet. So this is from our second production cycle, where we had 385,000 individuals inside of one unit, where it's in 10 months, approximately 10, 11 months, it grew over 4 kilos and was ready for consumption. And of course, I have to make a fine picture here with salmon with 0 lice. We have not yet, and also in our third production cycle, we check for lice and salmon lice, and we have not yet found 1 salmon lice, which is something that we're very happy about. And also, we had to put this to a test, because you could say that, okay, maybe in this location there isn't that much salmon lice. So what we did is that we took some of the fish from the Watermoon and moved it 150 to 200 meters to an open net pen. And the results, as you can see from the blue column here, is from the fish that we took out of the Watermoon. And they had 3 delousing treatments at the same time as we had the rest of the fish inside of the Watermoon. So this shows that the Watermoon is effective for avoiding salmon lice. And also these 2 column is locations that's also close to this location in the Hardangerfjord. And then we have the sludge collection. That's also a very interesting part of this. From the second production cycle, we collected between 1,700 and 1,800 tons of sludge with a dry matter of 9.6%. So a bit less in dry matter. But at the same time, we use 1,400 tons almost of feed. And the result of feed used is 11.7%, which is above industry average feed used, which is around 8%. So from that, we can see that we have a stronger performance than, for example, some land-based facility of treating the partial part of the water stream. We also think that this means that the Watermoon construction is doing something right and is showing that it's possible to also do this in sea construction. And we experience it as very effective on the results that we've gotten so far, and looking forward to seeing results in the future. So here you can see, you can just explain the pictures here. That's the sludge treatment system that we have on the fleet that takes it down to a dry matter of approximately 10%. And then you have the boat that comes around when we have our tank filled up to collect the sludge and take it to the next step. So where are we now? This is at a production yard in Norway, where we are producing now 3 more watermoon units in full scale, because we see that this gives good results, and IDA is now investing in 3 more units. So that we are really excited about. This picture is only taken a few weeks ago, where we are producing the steel parts of the unit. And I think with that, I'll just say that this is kind of the core of what we're doing in Watermoon. We are documenting the results to keep improving, and also operations know-how. How do we work with this type of technology, this type of producement platform, and then keep on developing Watermoon, of course. Thank you.
Thank you so much, Christine. So not only that you're collecting the fish sludge, you have proven so far that there is no risk of the lice. And this, of course, is very good news. So hopefully now we have someone from the European Union listening and seeing this recording as well. So the potential is there. If we only will be able to also use the phosphorus that we recover, that will also boost the production. I will now turn to Vivi. Please give your reflection of what you heard so far, both from Manuel, but also from Hans, and of course from Christine.
Thank you, Per. Well, first of all, I want to say that I'm impressed that you are taking the environment part, the environment effects seriously, and really developing new ways of coexisting, that the industry can coexist with the environment, and an attempt of kind of decoupling the effectiveness or the industry from environmental damage. And maybe something that I wanted to say stemmed out of the what I heard here earlier. I don't have any kind of agenda to say that I would want more agriculture or more fish farming. My agenda is for the marine environment, and I really think that it's something that we commonly need to get together. So we should not be kind of struggling and fighting that who can pollute the most. We are actually in a situation where we cannot afford to pollute, and we should pollute less than what we are polluting. And we really need to make an effort to go into that direction. And what I wanted to show with my presentation was that even if we go down in the pollution, our results in the environment will still show with a considerable time lag. So it's time to do it now.
Yes, and I hear the same as you have presented. And was in Norway. I hear the same thing from Canada. We hear the same thing from Chile as well. So the challenge that the coastal areas are eutrophication, are causing the problem to increase the production, and even they need to reduce it. So we need to do whatever we can. I totally agree with you. Hans, your reflections.
Well, I think the introductions of Manuel and Vivi were really on spot in what we are interested in, looking at the drivers, looking at who can be part of this transformation. The Blue Transformation initiative of FAO is admirable, but as also Vivi said, what pioneering companies like IDA and Christina just showed, how they are leaning forward, how they see that growth is not we can do inevitably without facing the challenges and taking responsibility of those challenges. So we also saw some trends that the global aquaculture is in being more industrialized, but then again, like IDA, taking responsibility for their part of the blue acre, so to speak, the blue field, their coastal zone, leaning more towards regenerative practices and the recycling the feed that is going to be used, and the increasing need for feed to grow aquaculture, as we see the trend is. We cannot simply let the sludge be lying on the fjord bed and destroy ecosystems. We need to see that as a huge asset to continue the growth of aquaculture and sustainable food production.
We are running a little bit out of time, but I would like to have, before I hand over to UNEP and Vanjira now to give the closing remarks, I would like to have your reflection, Christine, what you have heard, and what are you thinking going forward?
First of all, I think this has been a really good seminar and really good presentation. And generally, from the presentations, I can see the need of new solutions to be a part of the aquaculture industry, Watermoon, but also other solutions to collect waste. And as the first presentation showed, that we should be growing, but we're not growing in this area, that really shows the need of to increase and really to look at these types of the sustainable solution. And also I noticed a quote at the end of Vivi's presentation: reversing takes as long as creation. And I also think that is a very important statement, and very important to acknowledge that we don't have years to start thinking about doing something. We have to do something about it, and that's what IDA is trying to do. And that takes for the future, that what IDA is working on is trying to get incentives for more developing of these kinds of solutions. With Watermoon, that has, for example, zero lives and very low emissions, it can definitely boost food production. And Watermoon is approved for producing volume of salmon that cannot be produced in open net pens, but it's only the beginning. We have to make it more attractive because it's super expensive to do these kind of things as a company. And to make a change, it has to be, we have to be able to expand. So, yeah.
During the session, I had a lot of requests for having the slides and more information. So the interest is huge from the participants. We also have some questions that we will reply to afterwards, so we'll make sure that you have the response. From Ragsel's side, I'm really happy. We heard this message for more than 10 years ago from the fish industry, but we understood we can't do this by ourselves. And we have one part of the solution, but there are many stakeholders that now they create the full circular. Please, Vanjira, I hand over to you to give the closing remarks from UNEP's side.
Thank you so much, Pa. So good afternoon, everyone. On behalf of UNEP and the Global Partnership on Nutrient Management, I would like to warmly thank our speakers for their insightful presentations and all of you for joining us today. Today's discussion has highlighted both the opportunities and the responsibilities that come with continued growth of aquaculture. Aquatic food systems do play a vital role in global food security, nutrition, and in people's livelihoods. But they must also address the challenge of nutrient pollution while contributing to solutions of the triple planetary crisis. One of the key messages from this webinar is that circularity must become a guiding principle for the future of aquaculture. Nutrient-rich waste should no longer be seen as something to dispose of, but as a valuable resource that can be recovered, reused, and reintegrated into productive systems. The AQUAPHOENIX project that has been showcased today has demonstrated how circular nutrient management can transform fish sludge into valuable products, reducing environmental impacts while creating new economic opportunities. At the same time, achieving this transition requires more than technological innovation. Circular solutions can only be scaled through the right enabling environment, such as supportive policies and regulations, access to finance and investment, strong governance, knowledge sharing, and collaboration across sectors. These enablers are essential to turning promising pilot initiatives into widespread practice. Today's discussions have clearly shown that innovation, science, and partnerships are key to building more sustainable and resilient aquatic food systems. On behalf of the GPNM, I would like to sincerely thank our co-organizers, NOS and AQUAPHOENIX, and the AQUAPHOENIX project team, as well as our speakers and our participants for contributing to this important conversation. We hope today's exchange has provided new insights, inspired new collaborations, and strengthened our commitment to advancing circular nutrient management. Thank you once again, and we wish you a pleasant day and weekend ahead.
Thank you.